Hello! In this video, we are going to prove the following theorem. Let A, B, and C be sets. Then, A is equinumerous with A. If A is equinumerous with B, then B is equinumerous with A. And if A is equinumerous with B and B is equinumerous with C, then A is equinumerous with C. Now, to say that a set is equinumerous with another set means, by definition, that there's a bijection from this set to this set. Right, so that's really what this symbol means. And we're going to prove that it has these three properties. Right, we're essentially proving that it's an equivalence relation. So let's start out by proving one. So really, given a set A, we want to prove A is equinumerous with A. In other words, given a set A, we want to show that there is a bijection from A to A. Well, we know of the identity function on A, right? The identity function on A is a bijection from A to A. So yeah, there is a function from A to A that is bijective, which means A is equinumerous with A. So that proves one. Now let's prove two. Our goal in two is to prove if this is true, then this is true. So let's suppose this is true. Since A is equinumerous with B, what this means is that there is a function from A to B that is bijective. And let's say that f is a bijection from A to B. And our goal now is to show that B is equinumerous with A. That is, we want to find a function from B to A that is bijective. And to do that, we're going to use the following fact regarding a function being a bijection. The fact goes like this. Suppose we have a function g from j to k. Then g is bijective if and only if the inverse of g is a function from k to j. And that's it. Now, since f is a function from a to b and f is bijective, it follows that the inverse of f is a function from b to a. And our claim is that the inverse of f is a bijection. If we can show that, then we have a bijection from b to a, which is exactly what we want. And to show that the inverse of f is a bijection, well, we're going to use this fact, right? And to apply this fact, let's call G F inverse, let's call J B, and let's call K A. So if we call G F inverse, J B, K A, it follows that F inverse is bijective if and only if the inverse of F is a function from A to B. So, to prove F inverse is bijective, all we got to do is show that F inverse is a function from A to B. But really, F is equal to F inverse. So, since F is a function from A to B, we can instead say that F inverse is a function from A to B. So, F inverse is a function from A to B. So, this means we can say that F inverse is bijective. So, we have a bijective function from B to A, which is what it means for B to be equinumerous with A. So, B is equinumerous with A. So, we have shown if A is equinumerous with B, then B is equinumerous with A. Exactly what we wanted to prove, so that proves 2. And lastly, we're going to prove 3. So to prove 3, we're trying to prove if this is true, then this is true. So let's suppose this is true. So, since A is equinumerous with B, this means there is a bijective function from A to B. And since B is equinumerous with C, there's a bijective function from B to C. So we can let F be a bijective function from A to B, and let G be a bijective function from B to C. Now observe that because F and G are both bijective, it follows that F and G are both injective and F and G are both surjective. But if you recall, if we have a function f from a to b and a function g from b to c, it follows that g compose f is a function from a to c. Furthermore, if you recall, if f and g are both injective, then g compose f is injective. If f and g are both surjective, then g compose f is surjective. So we have that g compose f is injective and surjective. Since g compose f is both injective and surjective, it follows that g compose f is bijective. So we have found a bijective function from a to c, which is exactly what it means for a to be equinumerous with c. And so we have proven if a is equinumerous with b and b is equinumerous with c, then a is equinumerous with c. And yeah, that's exactly what we wanted to prove. So this proves 3, and as a result, we have proven the theorem. And so yeah, that's pretty much it for this video.